All right, yeah, welcome back. We want to continue from where we stopped. So we want to look at another parametric test called one-way repeated measures ANOVA. One-way repeated measures ANOVA. So the one-way repeated measure ANOVA uses more than two dependent samples or groups. Don't forget, we have done one-way ANOVA before. Okay, and we have also done pair test before. So when you understand ANOVA, and you that one way or another rather, and you understand a peer test, you have no problem with this. This become easy. All right. What is a one-way repeated measures? It is otherwise known as a within subject ANOVA, and is used to determine whether three or more group means are different where the participants are the same in each group. It's actually an extension, okay, to the peer sample test. A statistical technique that extends the concept of the peer sample test. Right? So if you understand peer sample test, it's very, very simple to understand. No difference. Only difference is that a peer sample test deal with two samples or two groups. All right? Why this one deal with more than two? That's all. It means the same specimen in peer sample is repeated twice, first and second time. We call it pair because there are two. The first repeater, no, I gave several examples. Remember example of those who went for uh, 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 on those who travel for during their when you are checking the stress level of a staff in a company. Okay, we talk about those who travel on this so that you want to see their stress level. You test their stress level on vacation now. You test their stress level before they travel on vacation, and when they return back, you test the same specimen, the same subject or number of people, their stress level also, their PB. You test when they come back, so to know if there's effect of that vacation, that there's any effect of that vacation on the subject. So I gave several examples during that period, and you can see that I gave a example of subject like animals, that animals can be inoculated or injected with some kind of disease or cancer. Then a treatment is being administered to them. Why that is done, then you have tested before that time, and then after that time you now do some measurement again to compare whether the what they call it now, the maybe what you are trying to administer to them, it works on them. All right, maybe vaccine you are trying to administer to them works on them. So there are several examples under peer test which I have done. So you can go back and check it. So it is time based. It is time dependent. That's what I meant. It has to within the period. It has a period in between. Even though in your specimen or in your data time may not be actually be part of the sample or showing directly in your group, but mere looking at it, you know that this is time dependent. It has a period within this period and this period. It's always like that. So peer, peer sample test is always time based, time dependent. You have before, you have after, or you have time and after this time they do this. So it's always like that. So the same thing is extended here under repeated measure. In this repeated measure, you only different that you have more than two. That's all. Okay, you have more than two. That is repeated again. All right. So that's exactly what we're talking about. So here, it is typically reserved for situation where there are three or more levels, right? This is because a peer sample test is generally preferred for comparisons involving only two levels. That is what I just explained now, okay? That is preferred. So if you have two levels, just use your peer test, no problem. But when you have more than two levels, then you have to extend it to one-way repeated ANOVA. So for this reason, the groups are sometimes called related groups. So the groups we are called related groups because they are dependent. Okay, the same thing with peer test. It's a dependent groups. They depend on each other. You cannot do them combine them together like that, like a independent group like the one we did before. No, that was for unpair. So this one is dependent. The one before is dependent on the one after. That's what it means. In unpair, you can have a group called gender. They're not dependent on each other. It is called independent group. Male and female are not dependent on each other. You see that? So that is different. But in this case, these groups are dependent groups. So you will most often come across this situation for two reasons. One, participants have been measured over multiple time points to see if there have been any changes. Maybe in what you're administering to them, maybe in the PB, or in their stress level, maybe there are changes after some kind of maybe vacation or administration of some drugs or some vaccination or some supplements, whichever way if there are any changes. Then participants have been subjected to more than one condition or trial, and the response to each of these conditions is to be compared. So that's where you find this kind of sampling or this kind of test. Now, for example, let me repeat some example here. I said something like this before under peer group ANOVA, paired test, but not exactly. I try to extend it here now, okay, to understand now whether there is a difference in anxiety level amongst moderately anxious participants after a hypnotherapy program, which is aimed at reducing anxiety. Right. For example, we have three levels now with 3 times points. That's what it means. Anxiety immediately, that's first level. Anxiety immediately before, and 1 month after, and 6 months after the hypnotherapy program. So we have three levels. We have anxiety immediately before, and we have 1 month after, and we have 6 months after. So this one, maybe I can just say, maybe you can call it this can just call it maybe A, B, okay, or can just call maybe anxiety immediately. Can say maybe AI. Can call it one M, be 1 month, 1M. This can be 6 months, 6M. You can see that AM, 1M, 6M. AM means immediately, 1M means 1 month, 6M means 6 months. Maybe you cannot in your group, you cannot be saying aside immediately before, can be writing this long kind of a long this in your this thing in your column, your variable. No, you can't be doing this. Okay, you have to shorten it. So that's why I'm using that for you as a sample. All right. So in this case now, anxiety level is our dependent variable. All right. You remember that anxiety level that become our numeric variable that we are using to measure. All right. Why the independent variable is time, which we should just look at now. The variety of time we have here. All right. With 3 related groups, where each of the 3 times point is considered a related groups. So the first one is this before one, the second one is after 1 month, third one is after 6 months. These are the time difference in which the anxiety level is measured for the same specimen. So this same specimen was measured at this time point. The same specimen was measured at this time point. Same specimens come back again and measure at this time point. The same specimen, don't forget, the same specimen. So that is called repeated measure. Okay, so another example is that to examine changes in blood pressure in patients undergoing different stress management techniques. What are the techniques? For example, with 3 techniques like meditation, counseling, and exercise. So we have 3 levels again here. Okay, so here, blood pressure, BB, will be the dependent variable now, and that is a numeric variable now using for measurement. Okay, and the within subject factor will be the stress management techniques that we are talking about, which is 3 levels. So we have meditation, maybe you can call it MD, okay, maybe ME, meditation, CO for counseling, and EX for exercise. So you just shorten them, ME, CO, and EX. That's the 3 levels we have. Okay, so and here you have only 3 levels already, and you have BP as your measuring column. All All right, so now, and again, another example is to assess changes in productivity levels of employees in different office environments. E.g., within 4 environments, for example, we have open plan, we have private office, we have home office, and we have co-working space. So that there are 4 levels now, or 4 groups. Okay, so let me just use that word, 4 groups. So in this case, productivity level is dependent variable. So this one is what is measured. It's our numeric variable. That's what it means that we're going to use to measure. And dependent variable, our dependent variable and the within subject factor is office environment, which is 4 levels. Okay, so this is our dependent variable now. Okay, and our this will become our independent variable is this particular. Okay, let me say and the okay, let's say this the productivity level is the dependent variable, and the independent variable and the within subject factor is office environment. So that is just what I'm trying to explain here. So that is our independent variable. At the same time, it's our within subject factors. So we call it's 4 levels, all right? That is within office, which is a we can call it maybe OP, PO, HOCS. For example, now that's just when you are entering your data, just use that one to just use abbreviations to describe them, so that you not type long very content strings. So what are the assumptions? The same way peer group comes with the assumption, ANOVA comes with assumption, the same way also comes with assumption. All right. The first assumption is dependent sample. The sample must be dependent sample. That is first assumption. You understand what I mean by dependent sample? They must be dependent. So not like the previous those ones we did before that are independent samples. They must be dependent, which means they must be measured repeatedly. The same sample, the same sample again, first time, second time, and third time, or more. All right. That is dependent samples. All right. So normality is very important as well. The data should be approximately normally distributed and have metric scale level. All right. This assumption is especially important when the sample size is small, which means is a measuring data. Your normality is a continuous. The measuring variable there, for example, score, PB, they are continuous variable. That's what I mean. They are continuous variable. That's what I mean. The measuring the metric scale level. They are continuous variable. Okay. Don't just use any kind of variable there. They must be continuous variable so that they have measurements. That's what it is. So when you run them through normality check to see if they follow normality assumptions, then you know probably by running a Shapiro test or using a visualization. All right. So homogeneity of variance is also important. The variance in each group should be equal. So Levitt test can be used to check that. Okay. Also, we have what we call homogeneity of covariance. So don't forget, it is called sphericity. Right. The variance of the difference between all combinations of the different groups should be equal. This one is different from the previous one now. Okay, for equality, for combination of the groups. This assumption can be tested using what they call Machi test of sphericity. All right. So though this one can be checked also using in your analysis when you run your test, you see what they call GES to set that. So that's not a challenge. So no extreme outliers. So outliers can be disappropriate effect on ANOVA, potentially leading to misleading results. So we have to limit outliers. Not that cannot be outlier at all, but it must not be extreme. That's what we're talking about. Now let's look at an example here. We are going to use a self-esteem score data set measure over 3 times points. The data is available in the Datarium package we have used before. So it has many, Datarium package has many data sets there. We have used first esteem, before. So you have to use first esteem again. But this time around, it's going to be a little bit different. All right. So here we want to determine whether the mean self-esteem score has anything different between the 3 time points. Okay. So we are going to run this library again. All right. So we run our testing. So you can glimpse and see what I'm talking about. So when we glimpse, we have 10 rows, 4 columns. Look at the way that the data is look like. So this is the first sample, second sample, third sample, or first group, second group, third group. Okay, this is the factor now. The factor here is the score. These are the score of for different time for individual. Okay, this person now 1, 2, 3, 4, 5. This is the same person 10 times. All right, this same person, this 10 participant, for example. Now this is repeated for 10 times. I mean, repeated again for T1, T2, T3 for 3 times. The same participant. All right. So you understand what I'm saying? Like if you run this, for example, if you run this, okay, you see that you have 1 to 10 for T1, T2, T3, right? But let's say we run let me just I'm not saying it's going to be, let's view, let's use view self-esteem, right? Let's view. All right, see what I'm talking about. We have high DA. This is one person. So this person is done first time, second time, third time. The same specimen already repeated. Same specimen. This specimen 1 is done time 1, time 2, time 3, first time, second time, third time. Specimen 2, same person. Okay, the same person. So that is exactly how it is now. So just understand that. So let's just close that. All right. So here we can actually combine the time together as score. Right. You have done that before. Just use your library arithmetics. We can just say we can use a piping here. You can gather the key, call the time, and score t. Right. So you can follow the number. So you can remember when I was doing the first one, we used this same thing before. We use a matrix method to run our was that not in a Friedman test? Yes, Friedman test. Friedman. So we use this particular self-esteem where we pass this T1, T2, T3 in form of a matrix, and we also do it in form of a direct imputation using a variable in group form, where we now combine it together. So and we have the same answer. So in this time around, you can do combination now together the same way we did like that the other time. So we can just say, oh, let's factor it together, and we gather them. So we have done that now. We have grouped them. So the score T1, T2, T3. So that now we have if you check again now, let's say we check again here. So now it now makes more sense now. We have high D, we have time, we have score. That's all we have. So the T1 you are seeing now, T1 is this one, T1 for this, T1 for that, T1 for this. So it has to be arranged now properly. We have grouped them. This is how it's supposed to be. But that one was measured individually. That is why it's like that. So, but you can now combine it together now and arrange them properly. So this become your factor, right? Don't forget your factor now. Factor variable, which is and the ID is also factor variable because it's for individual. It's repeated. Yes, it's repeated. This repeated 3 times now. Okay, so that means you automatically you have 30. Okay, first time, second time, third time. Right? You have 30. Now, if you dim now, if you dim or you glimpse any one of them you do, it will give you your dimension of your. So you have 30 by 3 now. Okay, so that's exactly what I'm saying. Now, so we can now further plot and see. Let's do some plotting. Plot a ggplot box plot for this and see how it looks like. So we pass our self-esteem here ggplot as usual. Then our x variable is time, our y variable is score. Then we factor we don't need to put part factor there anymore because we already factor. You can see already factor here. So factor is not needed. So you can remove this. Okay. It was before when there was no this thing that it was added. So can be removed now. Okay. So we have fee, color of time. You can also say color. You can say color time. So it won't be fee. Okay. It's the same thing actually. Okay. Don't worry. So but you can just run this. All right, so we don't need to show the legend because we already know that each of them is a T1, T2, T3. All right. This each in your time. All right, this in your time. So when you come to legend one, I will show legend. For now, we just want to hide the legend, so don't want legend to be shown. So we already know that this one is T1, this one is T2, this one is T3. That what it means. So we have only one. So we don't need to show the legend here for now. So the color is already separating it. For example, if I say if I remove this line, if I remove this one now, by default the legend will show by default. Okay, but we don't need the legend. You can see it's showing here time, but time is red, the color is rather red, green and blue. So it's already shown here, so we don't need it. That's why I that legend was hidden. All right, so you don't need that anymore. So it's not necessary here. So now let's compute some summary statistics, okay, of the self-esteem score by groups. Our group now is time. Don't forget, that's our factor variable is time. Then we want to look at the mean and standard deviation. All right. So we can run our piping again and self-esteem. If you are not understanding the piping, you can go and listen to one of my video in piping under statistics and how. Okay, that to make something clear. I make it very basics for you to understand it at elementary level. So I didn't make it complicated at all. I make it very simple so that a beginner can follow. Now here self-esteem here is passed our data set. So we group by time. So time is our factor variable or categorical variable. Don't forget categorical variable now. All right, so we can use this method or this method. So this method comes from our status here from this particular library. All right, okay. But this one come from tidyverse. Okay, tidyverse. Okay, it's actually deep light R. Okay, in tidyverse. So tidyverse come with some other library called like deep light R. So this one come from deep light R actually. So this one come from this R stats. Okay, so we can use any one of them if you prefer. So they will have the same result. Okay, this one will give you the details. All right. In case you are not familiar with this, you can just use this as usual. So when you run this, you have the T1, T2, T3. You have the score here. So number is 10 times each for each person. We have the mean of 3.14, 4.93, and this and so on. So we have SD, standard deviation. So if you want to use this method, okay, you are welcome also. So this one is our usual normal method. Just summarize. We pass our N here, our mean here, our SD here for each score. So our self-esteem is our table. Then our grouping variable is our time. So just pass it here. Just run it like this. So we're having the same here, time t here, n number of n is here, so mean is here, sd is here. So you can see we have the same mean here. Okay, we have the same. So we don't need we don't need score variable actually. So but it's showing you that is what is used to measure. Okay, so that is what we have here. So because we want to see score here, that's why I put it here. So you can remove score if you don't want score. All right, so just type equals to mean. But we put it here because we want to show that the score, the mean we are looking at is based on score. The SD we are looking at is based on score. That is why it is supplied here. Okay, so that is very important. All right, so let's check assumptions now that we have understood this. Let's check assumptions. We can see that the mean is slightly different from different time. You can see they are not the same. Okay, the mean. Each mean for different time is different, it's unique. All right, so that one is clear from the both the graph or the plot here and the result we have here. But is this significant? I want to see this difference. Is it significant? So we can check our outliers first. Let's see. Okay, the first assumptions rather. Want to see outliers, so we can run as well outlier score from this particular library for this from this library now, uh, this house statics, we can see, check our outlier here. Okay, so we'll just say identify outlier by score. Okay, so just run this. It's very easy for us to do that, so you don't need to waste time. So you can also observe maybe your plots and see maybe a box plot. You can see here we have one, we have one here, so it's not extreme. Okay, it's not extreme. So you can see our time t1. So we see outlier in t1 and t2, which is all your t1, t2. You can see both of them have outlier 1 1. Okay, so how many? We have 6 here, we have 2 here. No, sorry, the id. So now score uh is 2.05 to 6.09, the outlier. Okay, this score. Then is outlier? Yes, true. Is it extreme? No, false. These are logical variable now. We are saying that they are outlier, yes, each of them. But is the outlier extreme? Say no. So it passed. So the outlier is not extreme. So you don't need to worry. So just go ahead. You can for second assumptions. Don't forget we have been doing the assumption before this particular Shapiro before, so we don't need to bother so to worry. So just pass your data in. Data are non-distributed, that's a H0. Data are non-normally distributed, that is a H1, that is a alternative hypothesis. So that is what you have been doing so far. If data is if it is significant, okay, it is significant, which means if your p-value is less than 0.05, that's what it means. It means you are what are saying that the test failed. That's what it means. Okay, I mean data are not normally distributed. That's what it means. But if you're not significant, which is your p-value is greater than 0.05, data are normally distributed. That's what it means. This is the structure of the hypothesis for both Levin test and the Shapiro test. Even other ones, same. Okay, for normality check, they are the same. All right, so let's run a self-esteem here by group. Okay, can run here by group here. So just nobody pass our score in here. See by time, group time. So you can see both of them 0.85, 0.174. So for each t1 we have, because each t is a different score on its own. This one group, second group, third group. Okay, so that is why it's like that. So you can just use by group to test it, or you can just pass it one way direct, the way you used to do before. Just do like this. So it's still the same. We have 0.157. So it's also not a significant. All right, you understand? So which means we pass the test for Shapiro. All right. Assumption 3 is veracity, which can be done later. We are going to get that one very soon by using the function get ANOVA table. In this in that library, we can extract the ANOVA. We use to extract the ANOVA table, the greenhouse Giza specificity correction, otherwise called generalized eta square, is factor violating the specificity assumption. So this we are going to get the GES, right? GES will show us if it is significant or not. If we meet assumption for sphericity, we know that using GES, right? This generalized eta square will show in our ANOVA table. All right, so let's go ahead and plot compute the one way ANOVA repeated measure. So let's just call it result. ANOVA test, we pass our data, call self-esteem, our DV, we call it a DV simply means dependent variable. Don't be confused. Dependent variable, DV, dependent variable. All right, so we pass it here, and don't forget that is score. Okay, our independent variable is our factor variable. Take note, which is our time. All right, so our DV score, which is a so we have a WID here. So this WID here is our individual person ID. The same way we did for peer test. All right, peer test. The same way you have a ID here. ID is person 1, person 2. All right, that's what it means. So we have within time. Within time, this within is our factor variable. We call it within effect now. All right, our factor variable. We are doing it. That's our independent variable. Okay, factor variable is time. As categorical variable we have there. Then effect size, you can say effect size equal to GS. This one can be removed. It's by default, it's GS by default, okay? Right, so we can remove this. Right, by default it's GS, so don't need to put it here. So you can run this line of code. All right, it's run. So we can now see get ANOVA table now and passing our result inside. So we can see is GS, right? 0.82, which is it's less than 0.05. I mean, more than 0.05 rather. So which means it passed the test for sphericity. All right, that's what it means. Okay, now we have our time. We have effect here. So our effect is time. So our degree of freedom is here. We have our F value. We have our P value equal to 0.000 is very high P value. So this is type 3 test now. Okay, so that is the result we have now. Now the self-esteem score was statistically significant, really different at the different time points during the diet. All right. So we have a F55 P less than, so we have a P value less than 0.01, eta 2, which is our what we got here, GS 0.83 approximately, right? So GS is generalized effect size, right? So amount of variability due to the within subject factors. Okay, that is our GS size now. So we can further do post hoc test, okay, by looking at pairwise of this because we want to say, okay, this is significant now. So which particular one that is significant among this time factors, which one of them has effect more on the score? Okay, so we can just do what you call pairwise test. Okay, so we are doing multiple pairwise tests between the levels of the within subject factor. Here our factor is not time, don't forget. So we can run the self-esteem pairwise test here. Then we can pass our score and time together in. So pair is equal to true because it's really pair, like the one we did for a PRT test, is the same. So our adjustment can be Veroni, can be BH, can be, which is a Benjamin. So you can use any one of them. You can use FRD and that. So let's run this. You can see that here we have our group here, group 1, group 2. So this one against this against this against this. All right, that's what I mean. So for each set, they are all 10. Statistics, we are having this, and the degree of freedom is this. Let me just arrange so that you can see properly. Something is hidden here. Let me run again. All right, so that you can see the p value we are having here is normal. The normal p value and adjusted p value is the normal p value is highly significant. You can see when they are adjusted using Bonferroni adjustment, which is very conservative and very stringent, we have this significant p value. So this is also significant. You can see. So you can see these are the signs here. Asterisk, this highly significant, followed by this and this. So this is what I'm talking. So all the pairwise differences are statistically significant, which means T1, T2, T3 are all in pairwise form. They all has effect on the score. So the self-esteem score was significant, different at the different time points. Okay, we have this, okay, as our result, okay, and generalized eta is equal to 0.83 approximately. All right, so the self-esteem score was significant. Okay, that is just what I just repeated now. Post hoc analysis within a Bonferroni adjustment revealed that all the pairwise difference between the time points were statistically significant difference at p than equal to 0.05. So our equal to be p less than 0.05. Okay, not equal to so this is our for Bonferroni adjustment, you can see equals to, okay, no problem. So for Bonferroni, so it's not because the test itself is very stringent, so you can see make it equals to. All right, so that is just that for now. So you can see that this is a one-way repeated measure ANOVA. So you can go ahead and go through it. You can pass your data in to run and test. Since you understand the structure of data set now, there's no problem anymore. The challenge we do have most times is when you don't understand the structure of data set you can use for this type of testing. So we don't know how to carry it out. So now you understand the kind of data you can use for this in case you have such in your experiment on your research. You can go ahead and do the test. Thank you so much. I will see you in the next class for the next lecture. If you are not yet subscribed, you can go ahead and do that so you can see more of this classes.